Radiation. The model of the ether proposed in this work considers that light is a wave-like disturbance carried by etherinos. From a source of light emerge in turn excesses and deficits of etherinos, with some specific periodicity and distribution of velocities. The etherinos do not interact with themselves, like in a pressure wave, but travel instead all the way from the source to the detector. The disturbance alters periodically in space and time the distribution of velocities of the etherinos of an otherwise undisturbed ether. The apparently corpuscular behavior of light in some scenarios should be explained by the cooperative effect of the pertinent etherinos on the elementary detectors, usually electrons, of the target. As has been said, from the electron emerges a redistribution of etherinos that has an axial symmetry. The axis of symmetry of its redistribution is called the PRA, preferred redistribution axis, of the electron. The plane perpendicular to the PRA passing by the center of the electron will be called the equatorial plane of the electron. Summarizing from previous articles, the redistribution of the electron is the excess or deficit of n-type etherinos of a given speed emerging from the electron along a given direction by unit time, by unit solid angle, and by unit speed interval. A redistribution is caused when an elementary particle bathed by its local ether switches etherinos whose type is different from the type of the matter of the particle into etherinos of the same type. For example, the electron, which is made of n-type matter, switches p-type etherinos into n-type etherinos. The electron creates a redistribution with an axial symmetry because the electron's cross-sections to interactions with the etherinos have by hypothesis an axial symmetry due to some internal structure of the electron. The model considers that the function shown in expression number 1 is a typical etherino-particle interaction cross-section of an elementary particle. In this expression, V sub r is the speed of the incident etherino relative to the particle. Alpha is the angle that the semi-direction of the etherino makes with the equatorial plane of the particle. B is a constant, which is the same for all ordinary elementary particles. A sub p is a function with axial symmetry, specific of the elementary particle. It can be deduced that the redistribution of etherinos created by a particle P that has a switch cross-section sigma sub sp and is at rest in a canonical ether is the function shown in equation number 2, where ρ is the canonical distribution of etherinos speeds of the ether, including both types of etherinos. It will be supposed in what follows that the axially symmetric function A sub p in the switch cross-section of the electron is much bigger along the polar directions than along its equatorial directions. The redistribution of the electron will therefore also be stronger along its poles and weaker along its equatorial directions. The following picture number 1 is a sketch of the electron's redistribution with the PRA axis joining the two poles. It will also be supposed that when an electron moves with constant velocity relative to a rectilinear reference frame, its PRA does not rotate. The model calls rectilinear to those reference frames that exist by hypothesis in which the etherinos move in straight lines at constant speeds. When an electron is subject to a gradient of etherino impulses, that is, when the electron suffers a force, its PRA tends to align perpendicularly to the gradient and to rotate. This is shown in figure number 2. Like in mainstream physics, the electron is assumed to have an intrinsic angular momentum, and the alignment and rotation of its PRA should be interpreted as the natural way to conserve the angular momentum when the electron suffers a net force and hence an acceleration. The vector characterizing the rotation rate of the electron's preferred redistribution axis, PRA, will be called the intrinsic rotation vector, IRV. It must be here understood that the rotation axis is perpendicular to the PRA. In figure number 3, the preferred redistribution axis of the electron is represented by a segment whose two semi-directions have been distinguished by different colors. The figure represents such PRA in two different orientations. In changing from the orientation A sub 1 to the orientation A sub 2, the PRA performs a rotation. Its rate of rotation is represented by the up-pointing vector IRV. Some examples of emission of radiation. As is well known, an electron that moves perpendicularly to a uniform magnetic field suffers a force called the Lorentz force that compels the electron to describe a quasi-circumference in a plane perpendicular to the magnetic field. Due to the force exerted by such magnetic field, the electron suffers a specific shower of neutrino impulses that forces the PRA of the electron to rotate in space. The experimental facts about the radiation emitted by the electrons in this scenario suggest that when an electron performs such magnetically compelled circumferences, the intrinsic rotation vector of the electron aligns itself at all times with the electromagnetic Lorentz force. See figure number 4. Furthermore, if the electron travels along the circle at non-relativistic speeds, the experimental facts, like for instance the frequency of the emitted radiation equals the orbital frequency, imply that the modulus of the rotation vector must be equal to half the angular speed of rotation of the electron along its circular trajectory, and therefore, since the redistribution of neutrinos emerging the electron has a maximum at both semi-directions of its PRA, an external observer placed far away will see a relative maximum facing him once in every orbit of the electron. Figure number 4 represents the circular trajectory of an electron in a uniform magnetic field. The electron goes through the successive positions 1, 2, 3, 4, 5. The trajectory lies in a plane parallel to the YZ plane. The quasi-circular trajectory of figure 4 corresponds to an electron, negative charge, that moves perpendicularly to a uniform magnetic field B directed along the semi-direction X. The arrows represent the orientations of the electron's intrinsic rotation vector that, as has been said, remains aligned with the force acting on the electron. When an electron performs an orbit acted instead by a centripetal force, for example when it orbits a nucleus due to its electric attraction force, the electron does not always radiate, like for instance in the so-called stable orbits of the atoms. These cases can be modeled supposing that in these orbits the PRA of the electron remains aligned at all times along the same spatial direction. See an example in figure number 5. A faraway observer will always see the same angle between the direction of observation and the PRA of the electron, and will therefore not detect any periodically varying distribution of neutrinos. The model cannot yet explain with its paradigms why the electron's PRA would maintain its space alignment in some special atomic orbits. When an electron is fired into a piece of matter, it suffers a deceleration, during which it is known to emit radiation, called Bremsstrahlung. The deceleration is supposed to be caused by the non-zero electric forces of the nuclei and electrons of the target that dominate at short distances, since in the case of neutral matter, the cancellation of the net force due to the addition of the forces exerted by the positive and the negative electric charges is only effective at long distances from the target. On the average, the force causing the deceleration of the electron acts along the opposite semi-direction to that of the initial velocity of the projectile electrons. This stopping force corresponds to a gradient of neutrino impulses along the direction of the force. The thesis is again that due to this gradient, the PRA of the electron is forced to rotate with its IRV aligned with the force. This alignment explains that for electrons of speed much smaller than the speed of light, an external observer detects radiation mainly along the directions perpendicular to the average deceleration. See figure number 6. The case of non-relativistic electrons accelerated by a uniform electric field, like for example electrons traveling between two plates of opposite charge, can also be pictured by figure number 2, in which the radiation emitted by the electrons has its maximum along the directions perpendicular to the electric force, and hence to the acceleration of the electrons. When electrons move alternately up and down a rectilinear conductor wire, like for example in a radio antenna, in response to an applied potential difference whose semi-direction is changed with a given frequency nu, it will happen that the intrinsic rotation vector of the conducting electrons will also change its semi-direction with the same frequency nu. In many cases, the PRA of the electrons will only rotate small fractions of p during a period of the applied potential, and it can be expected that the dominant frequency of the emitted radiation will also be nu, and in this case will not be imposed by the magnitude of the oscillating acceleration of the electrons. When a constant electric field is applied to a neutrally charged body, its electrons rearrange their positions and speeds within the body and quickly stabilize in states in which they suffer a null average electric force, because in those arrangements the electric force of the external field is cancelled by the electric forces of the neighbor charges. Therefore the body will not radiate, since its charges suffer no net gradient of heteronychial impulses. A transversal force of the model. It has often been argued that if the ether is the medium for the transmission of waves, it must have the mechanical properties of rigid solids, since only then it can sustain transversal waves with which the polarization features of light can be explained. It is here argued that an ether of heterinos that has more in common with a rarefied gas than with a solid is also able to exert transversal forces and to implement the polarization of radiation. An heterino traveling from an emitter E to a detector R along the straight line ER imparts an impulse to the detector. Let the reference frame of description be one in which the emitter E is at rest. The impulse of the heterino on the detector will also have a component perpendicular to the straight line ER. If the elementary detector, call it P, for example an electron, suffering the collision, is itself moving with any velocity u that has a non-zero component along a direction perpendicular to ER. In the reference frame of description associated to E, see figure number 12, consider that P is an electron forming part of the macro detector R that at the epoch of evaluation of the heteronymical impulse is crossing the axis X of the description frame. U is the velocity of the elementary detector P. V is the velocity of a neutrino moving along the direction X and colliding with P. The heteronymical impulse given to an elementary particle P by a neutrino that collides with it was defined as shown in expression number 12, where v sub r is the velocity of the neutrino relative to the particle P. H sub 1 is a positive constant. Therefore, unless the direction of the velocity u of the target electron is coincident with the direction emitter detector, or unless the speed u is zero, the detector will suffer a transversal force. It must here be understood that the source of forces, in this case an emitter of radiation, exerts a transversal force on a detector when the force suffered by the detector has a non-zero component along a direction perpendicular to the straight line emitter detector. The transversal component of the impulse given to the elementary detector P by the neutrino of velocity v is given in equation number 14. The minus sign in equation number 14 indicates that the transversal impulse acquired by the target electron P acts in opposition to the transversal component of its velocity u, and therefore tends to decrease its transversal speed. As said in a previous article, when a neutrino performs an impulsion collision on an elementary particle, the particle suffers by hypothesis an increment of velocity given in equation number 15, where mu is a constant specific of the impulse particle that can be called its inertial mass. V sub r is the velocity of the neutrino relative to the particle. And therefore, in the case of figure number 12, the particle P suffers a decrease of its transversal velocity component given in equation number 16. Considering that the particle P is receiving by all directions from its surrounding ether and matter a great number of colliding neutrinos, suppose now that instead of receiving from the source E an excess of neutrinos, this source removes neutrinos from the ether that would reach P if the emitter was not present. Suppose that the velocity of a given absent or missing neutrino relative to E is again v, and that therefore its velocity relative to P is v sub r equals v minus u. Then, as seen from P, the effect of removing a neutrino of velocity v sub r from the balanced shower of neutrinos that P was receiving from all its directions is equivalent to adding to that shower the impulse of a neutrino of relative speed minus v sub r, whose value is given in expression 17. The transversal component perpendicular to the direction ER of such impulse is given in expression number 18. And therefore, in the case of a missing neutrino, the particle P suffers an increase of its perpendicular to X velocity component given in expression number 19. Notice that the decrease or increase of the transversal velocity of P due to an extra or a missing collision of a neutrino does not depend on the value of the speed of such neutrino in the reference frame of description, but only on the velocity u of the detector P at the epoch of the collision. This is evident considering that in the reference frame of description, all the neutrinos, whatever their speed, traveling along a given direction, have by definition a zero velocity component perpendicular to such direction, and therefore the transversal component perpendicular to such direction of the velocity of any such neutrino relative to the moving particle is made up entirely by the transversal component of the particle's velocity u. Therefore, if a detector of radiation receives a balanced flux of neutrinos by all its directions except by a specific one by which it receives a non-balanced flux, then the transversal velocities of its electrons will increase or decrease according to whether the flux along the semi-direction in which the electrons perceive the disturbance is smaller or greater than the flux that they receive along the opposite semi-direction. These transversal forces of the model are somewhat trivial, but they may become dominant if the electrons of the detector are not free to move in the longitudinal direction. Polarization of light. The model is at this stage unable to describe in a consistent and detailed way the polarization of radiation, but considers that with the paradigms proposed below, an ether of neutrinos is able to implement the main features of polarization. It seems plausible that linearly polarized light corresponds to wavefronts, or more precisely planes of equal phase, that are not strictly perpendicular to the ray, but make a small angle with a plane perpendicular to the ray. Consider the following two examples of linear polarization. In the first example, see figure number 15, the wavefronts are orthogonal to the plane xz and make an angle psi with the plane xy that differs from a right angle. This case would correspond to what mainstream physics calls linearly polarized light along the direction y. It is in which the electric vector of the electromagnetic wave remains parallel to the axis y while it oscillates in amplitude. This wave would reflect in the plane of a dielectric oriented as in figure number 15, in which the plane is orthogonal to the plane xz. In the second example, see figure number 16, the wavefronts are orthogonal to the plane xy and make an angle psi with the plane xz that differs from a right angle. This case would correspond to what mainstream physics calls linearly polarized light along the direction z. This wave would not reflect at the Brewster angle in the plane of a dielectric oriented as in figures 15 and 16 orthogonally to the plane xz. Other features that are considered of interest to describe the polarization of light within the model are the following. Consider an emitter E of radiation with its emitting electrons suffering accelerations along the direction z. The left part of figure number 17 sketches this emitter in which two of its electrons have been represented with our PRA in red color. This example corresponds to what modern mainstream optics would identify as linearly polarized light along the direction z. Consider a detecting screen R facing the emitter. See the right part of figure number 17. The PRA of the emitting electrons remain parallel to the horizontal plane xy during their rotations, and therefore the global heteronychal redistribution of these electrons behaves like a beacon of neutrinos that is directed periodically towards the detecting screen. The dots on the screen of figure 17 represent the rate of heteronychal impulses suffered by the detector at some given instant. At such instant, the rate of impulses reaching the right part of the screen happen to be greater than that reaching the left part. That is, there is a gradient of impulses on the screen along the direction y. The magnitude and semi-direction of such gradient will change periodically in time, and this will be so whether the PRA of the emitting electrons perform full rotations in a continuous way, for example due to a long-lasting acceleration, or only fractional rotations due to an oscillating acceleration. On the other hand, the rate of heteronickel impulses reaching at any given instant the upper part of the screen will be at all epochs approximately equal to that reaching its lower part. In other words, there is no gradient of impulses on the screen along the direction z. The fact to be underlined is that in the model, a polarized radiation implemented by a lighthouse-type emission of heteronos singularizes on the screen, or more generally in space, a symmetry plane, the xy plane in the case of figure number 17, defined by the direction of the gradient of the heteronos and by the direction of the ray. Since this plane is the one swept by the oscillating PRAs of the emitting electrons, it will be called in what follows the sweep plane. The radiation based in an ether of heteronos exerts on the detector first longitudinal forces along the direction emitter detector, whose strength oscillates in time at the frequency of the detected wave, and second, exerts transversal forces that in turn increase and decrease the transversal speed of the elementary detectors. In the electromagnetic mainstream description of radiation, there are no longitudinal oscillating forces, although there is a radiation pressure along the Poynting vector. To confirm the existence of the oscillating longitudinal force of the model, an experiment could perhaps be performed in which a plane detector, for example a mirror, rotates in synchrony with the frequency of the wave. Varying the phase of rotation of the mirror relative to the phase of the arriving wave, it could perhaps be observed that the detector suffers a net force that varies in a way that is not predicted by mainstream physics. Figure 18 represents a scenario in which the emitting electrons suffer accelerations along the direction y. That acceleration makes their PRA rotate in the plane xz. The screen detects now an oscillating gradient of heteronos impulses along the direction z, whose magnitude and semi-direction changes periodically in time. There is now no gradient of heterono impulses on the screen along the direction y. This case corresponds to what mainstream optics should identify as plane polarized radiation in the plane xy. Reflection of polarized light on the plane surface of a dielectric. Figure 19 represents a two-dimensional view of polarized light entering a dielectric, for example a glass. The plane surface of the dielectric, drawn as a thick solid line, must be imagined to be perpendicular to the paper. The ray bends due to refraction when entering the dielectric, but in this example the sweep plane does not reorient in the dielectric, but is always the plane xz of the paper. That would be so if the electrons of the dielectric are favored to move in the direction perpendicular to the xz plane due to the addition of the radiation forces with the internal reaction forces in the dielectric. It seems therefore plausible that in the arrangement of figure 19, the electrons of the dielectric re-radiate in the direction of the reflected ray. Figure 20 represents a three-dimensional view of polarized light entering a dielectric whose surface is again perpendicular to the xz plane. But now the sweep plane of the emitter electrons is the xy plane. This case would correspond to what mainstream physics calls light polarized in the xz plane. The sweep plane tilts a small angle after entering the dielectric, in the same amount as the incident ray tilts into the refraction ray. The PRAs of the dielectric electrons, although they still rotate in the sweep plane, they now never point in the direction of the expected reflection ray, and there is therefore no reflection of light. Those intrinsic rotations of the electrons of the dielectric proposed in figures 19 and 20 result, as said above, of adding the oscillating forces of an incoming wave that has symmetry features to internal reaction forces in the dielectric cannot be justified by the model at this stage of the description. Notice nevertheless that the induced rotation is different from that of a free electron suffering a driving heterodynical force, because the electrons of a dielectric are not free, but bound by internal forces to the neighbor matter of the dielectric.